Welcome to binomial distributions. Now, binomial distributions are just a specific, special version of a probability distribution. And just like it sounds, binomial, right? Bi meaning two. It's just a probability distribution where there are only two categories, kind of a yes, no, true, false, success, failure type of thing. And the great thing about a binomial distribution is any set of data or any type of experiment can always be put into two categories. Even if you have something with multiple categories, you can always have category A and then not category A. So a simple example would be something like you could take political affiliation, which we know has more than two choices, right? Democrat, Republican, Green Party, Tea Party, Independent, etc., etc., etc. But you could take all of those and you could actually just create a binomial distribution by saying Democrat and non-Democrat. There's your two categories, or independent and non-independent, right? So you can always take multiple categories and force them into a binomial situation. So the binomial distribution ends up having a very powerful and widely used kind of importance. In order for something to classify as a binomial probability distribution, it has to have a certain number of traits. First and foremost, you have to have a fixed number of trials. So we're only dealing with discrete data, right? We have to have n number of trials. We have to be able to count up the total number of times we're going to try this experiment, whether it's flipping a coin or picking the numbers out of a hat or whatever it happens to be. The trials must be independent, which means every time we repeat the process, our previous results do not impact the probability of the next result happening. And that's going to get a little tricky for, let's say, if you were picking a bunch of people out of a group, right? Because as soon as you pick one person, there's one fewer person left in the group. So now the probabilities have shifted. But there are augmentations we can make to the procedure to make it seem independent. Each trial must have all outcomes classified into either successes or failures, right? They're your two categories. So every time you run the experiment, the result you get has to go into one of those two categories. But as I said with my previous example, it's very easy to force a multiple category situation into two categories where you can just call them success and failure, and you just define what a success is, and it can be multiple different outcomes can be considered a success, and multiple different outcomes could be considered a failure. So you could group them into two different groups. And then the key here, and this goes back to kind of the independence part as well, is that the probability of a success has to be the same from each trial to the next. In its simplest case, every time you flip that coin, if a success means getting tails, that probability has to remain constant throughout the trials. Well, of course it will, because the coin's not going to change. But you get the idea. If we were doing something else where we were picking somebody out of a group and they had to be a smoker, right? And being a smoker was considered a success. Then every time we pick that person out of that group, the probability that that person was a smoker would have to remain constant. And that's going to be difficult when you're taking somebody out of a group and then not putting them back, because now the total number of smokers has changed, the total number of people has changed, and therefore the probability has changed. But as I said, there are ways to kind of fudge the numbers if you need to, but with technology we don't need to do that. We would just use a different technique. Some of our vocabulary, right? We're gonna use success and failure instead of good or bad or yes or no. It's just the more commonly used terms for your two binomial groups. So when you see P of S, that's the probability of a success, and P of F is your probability of a failure. And of course, since these are two dichotomous groups and they make up the entire sample space, their probabilities have to sum to 1. So they are complements of each other, right? 1 minus P is going to equal Q, which is going to be the probability of your failure. So we're going to use P's and Q's. P for probability of a success, Q for probability of a failure. No, this is not where mind your P's and Q's comes from, but it is another example of P's and Q's. Okay, just like before, n is going to be the number of things, only here it's going to be the number of trials. X is going to be the specific number of successes in your trials. So remember, it's coming back to that X that we had in the probability distribution. So X is going to be the number of good results, right? P is going to be the probability of a success in one trial, not however many you're doing, but it's the probability of getting a success every single time you run the experiment. Q is the probability of a failure in one trial of the experiment, and we know that P plus Q is always going to equal 1. And then P, capital P of X, is going to be the probability of getting exactly X many successes from however many times. So if it was something as simple as flip a coin 10 times, what's the probability of getting exactly 3 tails? Then it would be P of 3, right? Where obviously getting a tail was a success. Be sure and when you're setting up your trials and setting up your experiment, you have to make sure that X and P both refer to the same category. So X is always the number of successes, and then P is always the probability of the successes. Sometimes it's not as clear as it sounds because a success isn't a successful thing. Maybe you're trying to figure out whether or not using cell phones causes cancer. And so you're looking back through a bunch of patient records and looking for patients who have some form of cancer. Well, then finding a patient with cancer is considered a success, even though nobody would consider having cancer as being a success. So your X would be number of patients with cancer. P would be the probability of having cancer, and you would just need to make sure that, even though neither of those things are great, they are going to be considered your success case. Okay? Now, this was the thing I was talking about forcing independence on something that really isn't truly independent. If, when you're sampling without replacement, so you take somebody out of the group, right, and then you take somebody else out of the group, and when you're doing that, the probabilities are changing every single time because you have less things in the group. I keep saying people, but it could be any kind of objects. If you're going to, let's say, take 1,000 sample of objects from a big population. N, remember, is your sample size, and then capital N is your population size, right? This is your population. So if the sample that you're pulling is less than 5% of your total population, then you can assume, right, you can kind of fudge the numbers and let the trials be independent. Even though we know they aren't going to be independent, the difference from one to the next is going to be so small because the sample is so small relative to the entire population that slight change in probability, you can go ahead and just ignore it and let it all be independent. But as I said, we also have stronger technologies to deal with these types of cases where we no longer have to do these kind of fudging of the numbers. Here's a good example. So we're going to randomly select an adult from amongst all adults. So just go out there and just choose someone on the street. We know from previous, let's say, surveys and things like that, that 85% of the population knows what Twitter is. So that means that if we just chose an adult at random, there's an 85% probability that that person knows what Twitter is. Now suppose we want to know what's the probability that if we went out and chose 5 people at random, exactly 3 of them would know what Twitter is. You're kind of asking, well, who the hell cares? That's kind of a stupid question. Yes, it is, but this is just a learning tool, right? But you get the idea. So I'm going to pick 5 people at random. We want to know what's the probability exactly 3 of them know what Twitter is. Is this a binomial distribution? And yes, if you go back and look at the rules, right? Is there a fixed number of trials? Yes, and in this case, what is our number of trials? And hopefully you're all saying 5 because we're picking 5 people. The number of trials is not 3. 3 is how many successes we're looking for, right? That's going to be our X. The trials must be independent. So that means, picking one person shouldn't have any influence on the other person as far as changing their probability. And yes, they're totally independent. Each trial must have outcomes classified into 2 categories. Well, either they know what Twitter is or they don't know what Twitter is, right? So either it's a success or a failure. So that's true. And the probability of a success has to be the same in all trials. And since we know 85% of the entire population knows what Twitter is, then doesn't that mean every single person has the same probability of knowing what? There's an 85% chance that this person knows it. There's an 85% chance that that person, right? So the probability remains constant. So it fits all the key criterion, and therefore it is, yes, in fact, a probability distribution. Methods for finding the probabilities. There are three ways, really three ways just to think about it. There's really only going to be one way we're going to use it, and that's going to be technology. So the first way is to use the formula. And I want you guys to take a second and look at this formula because it does help you understand what a probability distribution really does. So let's kind of go back to the previous example of picking 5 people, and we want to know the probability that 3 of them know what Twitter is. So here's my 5 dashes. 1, 2, 3, 4, 5, right? And exactly 3 of them have to know what Twitter is. So let's let the first 3 people know what it is. So it's going to be 0.85, right? 0.85 and 0.85, because that's the probability that a person knows what Twitter is. But if these last 2 people don't know what Twitter is, what would the probability of choosing them be? And yes, it is the opposite, right? The complement of 1 minus that, so 0.15, the 15% chance. Now look what we get. If we multiplied these together, because this is, to figure out the probability that this happens, we always have to multiply our dashes. So if you multiply all those together, that's going to give you a number that represents 3 who know what Twitter is and 2 who don't know what Twitter is. And if you look at this formula up here, it ends up giving us this piece of the formula, because the probability of knowing Twitter, our P, right, the probability of a success, was 0.85 in this case, and the probability of a failure was 0.15. So this ends up being, right, P, 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 Q, and Q. And if you multiply 3 P's together, that's P cubed, right, where X is the number of successes. In this case, we wanted 3 successes out of 5 trials. So you can see how these numbers give us that part of the formula. So this end part of the formula is just multiplying together the probabilities of those successes and failures. If we have 3 successes, then we end up getting 0.85 cubed times the probability of failure raised to the power of the number of failures we have, which in this case is 5 minus 3, right? 5 minus 3 and minus x, which is 2 of them. And that's the exact same thing we got with our dash technique. Now what about this? What's all this junk? Where does this come from? Well, hopefully you recognize that as one of our factorial formulas that we learned in our section on probability. And which factorial is that? Is that a permutation or a combination? And if you don't remember, pause the video and go look back through your notes, or you can wait a second and I'll reveal all. It is in fact a combination. That is the combination of n choose x, right? I know we normally used n's and r's when we did the formulas, but it's the same thing, right? So we have n many things and we're going to choose x many of them. This formula tells us how many ways we can take these 3 P's, right, these 3 successes and these 2 Q's, these 2 failures, and rearrange them. So it's counting up P, 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 Q, Q, but it's also counting up P, Q, P, P, Q, etc., etc., etc. Right? All the different ways you can rearrange those P's and Q's. That's what this combination does. It counts up all those ways. Well, if I rearrange the 0.85s and the 0.15s, put them in a different order, when I multiply them together, won't I still get this exact same number? Right? Won't I still get the same number that's going to be in that square, whatever that happens to be? Because we all know that A times B is the same thing as B times A. So if I rearrange all those numbers, I'm still going to get that same number. So if it turns out that I can actually rearrange them 10 times, then aren't I just going to get 10 of those numbers? Right, well, let's say that number was 0.2. I'd get 10 of them. I would add them all together, and that would be my probability, which would be a problem because it would be bigger than 1. So obviously it's not going to be that, but you get the idea. So this formula just says that, hey, this is the probability of X number of successes and the rest being failures. This is the number of ways that you could rearrange them, get them in a different order, right? And when you multiply those two together, that gives you the total of all of the probabilities of all those different arrangements. And that's the binomial probability formula. It's very simple. Don't worry about memorizing it because method 2 is using technology. Whether you want to use StatDisk or StatCrunch or Minitab or your calculators or Excel, all of these things will run binomial probabilities for you very easily. So there's no need to memorize that formula and use that formula. I like to look at the formula because it kind of helps us understand what's going on with the binomial formula. What's it doing? Why is it doing what it's doing? And it gives you a better understanding of what binomial probability really is. It's just telling you the likelihood of getting X number of successes out of N number of trials. So in this case, 3 out of 5 people know something. Method 3, using tables, don't even want to waste time with it. You know, that would be almost worst case scenario. Tables are very limited. You have to have the right number of x's and the right number of n's, and they're very limited. So it's only something you would use under very small circumstances. Obviously, the first thing we always want to do is try to use technology. If we don't have technology, a table would be easier under certain situations, but if the numbers don't allow it, then we have to fall back on using the formula. But unless there's a global blackout, why would we not have technology? Here is our example that we worked out before, right? The x's and the n's. 3 successes out of 5. Probability of a success is 0.85. Probability of a failure is 0.15. So we're looking for P of 3. We're looking for 3 successes. Here is everything thrown into the formula. N is 5. X is 3. Right? Our success rate is 0.85. Our failure rate is 0.15. Put in the 3. Put in the 5 minus 3. Calculate all that stuff out, and it ends up being 0.138, or almost 14%. And it's as simple as that. Again, technology will do it for us, lickety split. We've gone through this, right? That first number shows us the number of ways we can rearrange our P's and Q's. The second part gives us that probability of that arrangement of P's and Q's. And when you put it all together, it gives us the total probability. Now, just like any other probability distribution, we can calculate means and standard deviations. What's the other word for mean that we use sometimes? That is right, expected value. You'll also notice that these formulas are extremely simple, right? I mean, how could it get any easier than just n times p and then npq square root for standard deviation? So those are 2 of the easiest formulas you're going to see in this in your entire statistics career. So those might be 2 that you might want to memorize, but then again, who cares? Throw it into technology. Technology will do these for you as well. Just like before, we have the range rule of thumb, right? The unusual and usual stuff, and just like before, it's always your mean plus and minus 2 standard deviations. Here's an example. 95% of the world's population recognizes McDonald's, and that's actually pretty accurate. If you went out and just randomly chose a focus group of 12 adults, we could find the mean and standard deviation of the number of people in that group who recognize McDonald's. So in this case, our sample size is 12, and our P is 0.95, because that's the probability of a success. So the mean, right, is just n times p, and we would expect that out of a group of 12, 11.4 of them would recognize McDonald's. Now you're probably asking, how the heck do I get a 0.4 of a person? You don't. And that's something to realize, that an expected value doesn't always make sense in the real world. You can't have 11.4 people out of 12. But what the expected value means is that on average, if you randomly chose 12 people over and over and over and over and over again, sometimes 12 of them would recognize it, sometimes 11, maybe even sometimes 10. But if you ran that experiment over and over and over again, and at each time wrote down the number of people from that sample who recognized McDonald's, and then took the average of those results, right? You took the 12s, the 11s, the 10 that came up every now and then, maybe even had a group that only 9 recognized it, right? You add all those numbers together, divide by how many times you ran the experiment, then you would get an 11.4. That's what the expected value means, is that on average, if we ran this experiment over and over and over again, we would expect 11.4 as the average number of people who recognize McDonald's. Okay? And then the standard deviation of 0.8 when we round just tells us how spread out those numbers are, and it also can give us an idea of unusual results, which is what we do here. We take that 0.8, we multiply it by 2, we add it and subtract it from the mean, and we can see that on any on any given random selection of 12 adults, if we had 13 or more people recognizing McDonald's, it would be considered unusual. And you go, well, no, duh, because we only grabbed 12, so how could we have 13 or more? Again, silly result only because the numbers are so small. But on the other end, if we had 9.8 or fewer, that would be considered unusual. So if 10 wouldn't be considered unusual, but 9 would. So if we got a sample of 12 and only 9 of them recognized McDonald's, that would be considered an unusual result. And that's the end of binomial distributions. Now there is a related distribution called a Poisson distribution. And you can probably stop the video here if you're not going to do Poisson distributions in your class. But if you want to learn about a slightly different distribution, this one comes up a lot in the real world. It is actually a pretty important distribution, so hopefully you are going to cover it in your class. It's still a discrete probability distribution, just like binomials. The only difference is we use this distribution when we're looking at occurrences of some sort of event or experiment that happen over a specified time interval. So the random variable x is still the number of successes, right, or the number of occurrences of the event, but instead of it just being the number of successes out of n number of trials, right? And so we're not going to say we're going to go pick 5 people, what's the probability that 3 of them know something. It's the number of successes that we get over a time interval or some sort of interval, usually time. It can be distance, area, volume, or some other measurement, but time seems to be the most widely used version of this. So you can see how this would have a totally different application. It's no longer pick 12 people and find out how many of them understand or recognize McDonald's. It would be sit at an intersection and watch cars go by, and in a 1 hour time period, how many of those cars are hybrids, or electric or some sort of alternative energy vehicle. That would be a very timely question, no pun intended. And we would need to do a Poisson distribution to figure that out. Now the formula looks very complicated with that whole mu to the x times e to the negative mu all over x factorial, but those are actually very simple things, right? Mu is just your average, x is your number of successes, and e is that special number that you've hopefully seen before, 2.71828, blah, 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 similar to pi, right? It's an irrational number. So they're pretty easy numbers to deal with, and just like before, technology will do it all for us. The requirements for this distribution: the random variable x is the number of occurrences, just like before, only now it's over some interval rather than out of a certain number of trials. Your occurrences need to be random, they need to be independent, and they need to be uniformly distributed over the interval being used. So that means you can't have peaks and valleys. You can't be more likely to see hybrid vehicles in the first 5 minutes of the hour than the last 5 minutes of the hour. Or if you were going to do it over a week, it wouldn't be, you couldn't do this if it was more likely to see hybrid vehicles on the weekend versus during the week. So it needs to be uniformly distributed. It should be equally likely that a hybrid vehicle would travel through that intersection at any given point in time, for the example that we're talking about. The mean is very simply just mu, and the standard deviation is really simply just the square root of mu. Big differences between the two, right? The binomial distribution is affected by sample size and the probability, whereas the Poisson distribution is only affected by the mean. A binomial distribution has possible values from 0 up to n, right? Because you're only going to do n number of trials, so you either get no successes all the way up to all n of them. But a Poisson distribution has no upper limit. You could, in that 1 hour, no hybrid cars could go by, or you could have 1,000,000 go by. So there's theoretically no upper limit to x on a Poisson distribution. Here's a good example. So if we're looking over a period of 100 years, there were 530 Atlantic hurricanes. So we want to assume that the Poisson distribution is a suitable model. So that assumption means that hurricanes are evenly distributed over those 100 years, right? There shouldn't be a higher probability of seeing hurricanes in one year to the next. We want to find mu, the mean number of hurricanes per year. And then if P of x is the probability of x hurricanes in a randomly selected year, we want to find the probability that we have 2 hurricanes in a randomly selected year, which would kind of give us an idea of what's the probability that we have 2 hurricanes next year. So you can see how this could actually be a reasonable thing to do and kind of an important thing to do. Here are the numbers. Very simply, mu is just the mean that you would expect, right? Number of successes over total number of things. We had 530 hurricanes in the last 100 years, so 530 divided by 100, we had 5.3 hurricanes per year. That's the average. Now to figure out P of x, we very simply put those numbers in, right? So P of 2 is just mu, the 5.3 squared, times e to the negative 5.3 all over 2 factorial. You work it all out and it's 0.07. So there's a 7% chance of having exactly 2 hurricanes in one given year. And you might think, well, that's kind of small. But it is kind of small because this is the question of exactly 2, not 2 or more. So that's a totally different question. You can use the Poisson to approximate the binomial, but why would you, since we can already do the binomial? So you can ignore this and ignore this, and in fact ignore the rest of the slides. You can read through it and see how it used to be done, but this was really a technique that was only needed before technology came around, because this was actually a little easier to calculate, but ignore it. We'll just stop with this nice example of the probability of 2, and remember that's 2 specific. If you want to know the probability of 2 or more, you would have to do something completely different, and then of course the probability would be a lot higher. That's it.